Okay, I'm going to talk about floating point binary representation. And you have some references for this. There's this Word document, MWS underscore GEN underscore AAE under S underscore SPE, and then it says something like floating point. You can read this Word document. There's also a PowerPoint that's somewhat abbreviated that you can look at. So let me just hit some of the high points of this Word document. You should be familiar with scientific notation. What all that floating point binary representation is scientific notation in binary. Notice that scientific notation has a number part and a exponent part. We know it's always times 10 to the something, so all we need to do is specify this number part and this exponent part. Now you may wonder why scientific notation is necessary. Scientific notation actually improves accuracy of representation quite a bit. Another thing I'll point out here is that in this reference he's talking about representation of signed numbers, and in the Excel spreadsheets we've done so far we've only done positive numbers. But it's an easy matter to add a single bit, a single 1 or 0 that represents whether the number is negative or not. So I'm not going to include that in our spreadsheets. That is, however, an issue with the exponents because it makes a big difference whether the exponent is positive or negative. And there's another way around that, and I'll be showing you that how that works. Okay. So if you notice what you really want to do here, here you have this number. It has an integer part and a fractional part. And here the integer part has been multiplied down, so it's a number between 0 and 9. And that's how you represent scientific notation. You have a number between 0 and 9, or actually a number between 1 and 9, point, and then the fractional part. Now, with binary, it's quite similar. When you represent binary, you can see here that he's representing this base 10 number with this binary number. The first number is not a number between 1 and 9 because, of course, binary digits are either 0 or 1. In fact, for binary numbers, this first number here is always a 1, okay, because that's the only number between the only non-zero number between 0 and 2. So this first number will always be a 1. It's the first non-trivial place of the base 2 representation. Then you have these digits here, and then you have 2 times a exponent here. Now this exponent should also be represented in binary. Right? So what we have to do is we have to do 2 things. We need to represent this part here behind the decimal point, which is called the mantissa. We don't even need to represent this 1 because you always have a 1 here. So we need to represent this mantissa and this exponent. Now that's quite similar to you'll notice in this example that his mantissa is 1011. That's because he's only taking the first 4 places of this mantissa. In a more accurate binary representation, you would take all of these digits here. Okay. As we've seen before, you only have a limited number of places for your binary digits, so your accuracy is always limited. Let me introduce one more concept, which is the concept of machine epsilon, and he describes that down here. All right. The machine epsilon is a measure of the accuracy of a floating point representation. It's found by calculating the difference between 1 and the next number that can be represented. So that's the difference between any 2 representable consecutive numbers. And if you think about it, that's going to be equal to twice the maximum possible relative error. The maximum possible relative error occurs when your actual number is halfway between 2 consecutive numbers. Okay? And if the difference between two consecutive numbers is a certain value, then half of that value is going to be your maximum possible error. So the machine epsilon is a measure of the worst possible error that can be incurred by this binary representation. Okay, so you can read this here, and you can look at I recommend you look at the PowerPoint, which is a little bit more abbreviated, and you can also watch the video. So let's get started on our spreadsheet. Now, hopefully you already have your binary spreadsheet, because we're going to be using this again. Now we want to convert decimal to floating point binary. So that's going to be quite similar to the decimal to binary conversion. So in our usual practice, I'm going to steal what we've done already and select this part. I want to copy it and not cut it. Okay. And I'm going to put it down here below. I think that's binary to decimal, so we'll do it right here. Okay. And here, it's not just decimal to binary, it's decimal to floating point binary. Okay. Okay. We'll stick with that input number. Now, remember, we need both an exponent and a mantissa. So, and all of our exponents are in base 2. The exponent depends on base 2. There's a base 10 exponent. The base 10 exponent of this is 2. The base 2 exponent is going to be something different. So let me make all of this yellow, because I'm going to need that for my commentary. All right. So here we're going to put the base 2 exponent. And here we'll put the mantissa. Right. Now, how do you find the base 2 exponent? Well, it's the largest power of 2 that's smaller than this number. And again, let me reiterate that we're only dealing with positive numbers, so we only worry about the magnitude. Right. To find the largest power of 2 that fits in a certain number, the best way to do that is to take the logarithm base 2. For example, if you have 17, then the largest power of the power of 2, which is less than 17, is 16, which is 2 to the 4th. So if I take the logarithm of 17 base 2, you'll find it's going to be 4 point something, and you can see that it is. If I take, for instance, 35, 35 is bigger than 32. 32 is the largest power of 2 that is less than 35. And 32 is 2 to the 5th, so we would expect the logarithm of 5 base 2 to be 5 and then a decimal part, and it is. Okay, so here what I want is to get the exponent of this number. I'm going to take the logarithm base 2 of this number. Notice the description here in the LibreOffice, how it asks me for, this is the number I'm taking the logarithm of, and the second number is the base. So I'm taking the logarithm of this number, base 2. Okay. All right, now, the thing is that I only want the integer part of this, because I don't want the fractional part, I just want the integer part. So let me go back here and change that to integer part. And I get 8 here. So what that means is 2 to the 8th is the largest power of 2, less than 314. And if you know your powers of 2, 2 to the 8th is 256, and 2 to the 9th is 512. So indeed, this is correct. All right. Now, what is the mantissa? The mantissa is everything left over after you subtract out after you divide out by the maximum power of 2. So here I'm going to take equals this number divided by 2 to the power this number. And I get a number 1 point something. Now, it turns out that no matter what number I put in here, I'm always going to get 1 point something. That's because this is the largest power of 2 that is less than here. If this was 2 point something, then I could up this exponent by 1. So you can see I can do any number here. I could do that. You're still going to get, I could do 0.0004. It's still true that the first digit here is a 1. Notice here that the base 2 exponent is negative, because the largest power of 2 that's smaller than this is 2 to a negative power. All right? Since the first digit here is always 1, I'm just going to ignore that. There's no need for me even to convert that 1. So because I know that there's always going to be a 1, I'm just going to subtract 1, and that gives me my mantissa part. Okay? All right, now, in order to represent the exponent, here we have a negative number. Notice that here we have a whole number and a fractional number. We could use our spreadsheet down here. We could use this to convert the whole number and this to convert the fractional number. The problem is that our conversion only works with positive numbers, so we can't convert this negative 12. The way that this is solved is by biasing this exponent. What do I mean by biasing? Well, I'm going to add a number to this to make sure that this number is positive. And then I'll be able to represent it as a positive binary number. Right? So I'm going to put the biased exponent here. Okay. And that's the number that I'm actually going to convert. Now, usually the biased exponent is a power of 2 minus 1. And there are reasons for that. That's actually because you have a limited number of digits, and what that does is it makes an equal number of positive and negative exponents possible with a limited number of digits. All right, so I'm going to take here for the biased exponent, I'm going to take this number and I'm going to add 127. 127 is actually 2 to the, what is it? 2 to the 7th minus 1. Right. So why don't I just write it that way? 2 to the 7th minus 1, and you can see that it actually works. And that's my biased exponent. Now, as long as this number is bigger than 2 to the minus 127, I'm going to get a positive exponent here. So for instance, I could go 0.000003, like that. Okay. Still, the biased exponent is positive. On the other hand, I could go 3.00000 like that. Okay, and the biased exponent still is less than, well, it's not less than 127. So that's probably too big. So we cut it down a little bit. Okay, I'm not sure what's going on here, but I guess the positive can go up to 256. Right, but anyway, we get a limited number, both positive and negative, and we can deal with negative exponents by using this bias. All right, now what do we do? Well, again, we have a fractional number and an integer number, and we want to convert these two. So let's use what we've already got. Okay, I don't want to convert this number. I want to convert this number. So what I'm going to do is put the, let's see how this works. Let's see what this equation was. This equation, this part depended on those two. So you can see that we created this part by filling up. The original number was inputted down here. The number to be converted was input down here. So instead of this number, instead of that number, I'm going to input the exponent. Okay. And my conversion factor will automatically convert that to binary. Here's my binary representation of this number 148. Right. Now for the fractional part, what I want to do is convert the fractional part of this. And if we look at this, that was depending on this number. I want to convert the fractional part of this. Now this is already fractional, so I don't need to subtract the integer part. Instead of this a38 minus int a38, which originally was the fractional part of my number, all I have to do is put in this mantissa here. Okay, and that gives me the binary representation of the fractional part of my number. Now notice this original number has no fraction. Or I could do something like anything like this. There's still a mantissa. Why is that? Because when you represent this, you're dividing. You're dividing so that you only have one non-fractional digit in the binary representation. Okay. All right. Now, how are we going to represent this? Here we already have the integer part and the fractional part, but now this integer part has a different interpretation. This integer part is the biased exponent. It's not the integer part of the original number, it's the biased exponent. So I'm going to change this part to biased exponent. Okay. And then this part over here, the fractional part, this is actually the mantissa of the binary representation. So I'm going to take this. Actually, I need the decimal point also. So I'm going to take this, and we're going to cut. And I'm going to move it over here and paste it. And this is going to be the mantissa. All right. Now, why did I do it like this? Why did I leave a space here? Because as we mentioned before, the first digit is going to be 1. Okay, I know that automatically. And actually, what I'm going to do, I'm going to select this again. And I'm going to cut. And then I'm going to move it here. Paste. All right. The first digit is 1, so I'm just going to put a 1 point here. Okay. Oh, it didn't let me do that. Let me do something like this. I'll do 1 space point and see if it likes that. No, it still doesn't like that. Okay, let's put a couple spaces in front, something like that, and see if it likes that. All right, looks like I'm going to have to go back and do it my original way. So I'm going to cut this. By the way, to do that, when I did that, you can select this. If you right-click with the mouse after having selected, and you do cut like that, and then you click where you want it to go, and you right-click, and you click paste like that. This one wasn't there. Whoops. And I have to put a 1 here, and then there's a period here. Okay. Well, I'm going to put this 1 in dark green because that 1 is always there. It's not part of the conversion. Okay. And just to pretty things up, I want to make this all green because it doesn't look very symmetric. The way to do that is you can select one of these cells. You can copy. And then I'm going to select all of these cells here because I want all of these cells to be green the same way that this one is. And I'm going to do Edit, Paste Special. I don't want to paste all. I only want to paste the formats. So that makes all the cells green. Okay. So here is my floating point binary representation for my input decimal number. Okay, so I went through all those steps. Now comes the fun, is converting back to decimal from floating point binary. I mean, you really can't read this very well. You can't tell if I'm telling the truth or not. The way you can tell the truth is start from the binary representation and go back and recover the decimal representation. All right, so let me go ahead and do that. I'm going to select these rows here and copy. And then I'm going to, I'm not sure if you can see that, but I'm going to paste it. So I pasted the same copy, and we're going to make our modifications. Let me pull this up some to get a little more room. Okay. All right, now this is the conversion the other way, so I'm going to convert floating point binary to decimal. So let me just go ahead and click on this, select this, and I'm going to cut that and move it here. Okay, and I want to put a capital there. And then I want to convert to decimal, so I'm going to take this. Oh, why don't I just move the arrow? That would be easier. I'll cut that, move it here, and paste it. Okay. All right, so now, oh my goodness, what happened there? Okay, so we're going to have to change this format here. This should all be Arial. Let's go up here. Okay, let's see if that works. Okay, that looks a little better. Okay. I don't know what happened there, but it looked kind of interesting. All right. Now, we want to change these things around. This time I want this to be the input and the decimal to be the output. So we're going to work our way backwards. Okay. And in order to make the comparison, I'll do the same thing I did before with the conversion between a binary and decimal. I'm going to grab these to make sure that I'm doing it right. I'm going to grab these results from my conversion and feed them back and see I can recover the original version. All right, so this is F38. I'm going to put F38 in this cell. So before changing this, because this is part of an array formula, you can see this curly brackets here means it's part of an array formula. I have to select all of this and void it out. If I try to change this by itself, it will say you can't change part of an array. Okay, so the only thing I can do is I have to change this whole array at the same time. I'm going to delete that, and I'm going to put here, I forget what I said it was F38. So here I want equals F38. And then I want to fill this across. Some of you people know how to fill across. You can pull with a box like this. I generally avoid doing that, but you can if you like. It works fine in this case. Okay, I only want to pull across to here. So I'm going to do edit, fill, right. Okay. Then for the mantissa, I want to use the same mantissa I have over here. And this one was H41. So I'm going to have to void out this array here. And I'll type equals H41 here. And then I'm going to have to fill across here. Okay. Edit, fill, right. Okay. All right, so I now have my inputs that I want to convert back to base 10 base 10 number. Okay, so just like the first time when I converted back from binary to decimal, I'm going to have to move these binary digits back in their columns here. So this part is for the mantissa, and this part is for the exponent. Okay. So here we have equals, transpose, and then I've got these guys here. Unfortunately, he's covering up there. I don't know if I can do anything here. All right, let's try here. I want to select these guys here. Okay, and remember, I have to hit Control, Shift, Enter. It's not necessary to close the parenthesis. The computer is smart. Okay, and you can verify that these digits are the same as these digits. I don't need to worry about that one, and I'll show you why later on. Okay. Now, for these binary digits, those should be the same as these, so I'm going to select these guys and take transpose. And I have to take the transpose of this here. Control, Shift, Enter. Okay. All right, so my digits are good now. Now I'm going to erase this part because I need to reconstruct the fractional part from the binary digits, and I'll have to erase this also. And if you recall how we did that, to reconstruct the fractional part, here I took the 1/2 times the value here. And then here I took 1/2 times the value here plus the value here. If you don't remember that, you can go back and review the previous video. And then here I just did fill up. Okay. So we can check that that's actually giving me my same mantissa that I got before, so we're in good shape. And for the integer part, let's see what we did. I think we started at the top Well, we can actually see what we did here. Yeah, I'm pretty sure we started at the top. So here what we'd want to do is this is equal to this digit here. And then this one here was equal to 2 times this digit plus this digit. You know, digits, binary digits are also called bits. So you may hear me talk about bits. Edit, fill, down. Okay. We see we get 135, and that was in fact the exponent. Right. Now, since we're working our way backwards, let's void these out. Now the exponent is being derived from the binary representation. The value here should be equal to 135 here. And remember that this exponent was related to this number because this exponent was 2 to the 7th, was this number minus 2 to the 7th minus 1. So I'm going to have, here instead of, I have to go backwards, this is going to be equal to, x equals this number plus 2 to the 7th minus 1. Okay. Let me make sure I did this right. I think I might have made a mistake up here. So hang on a second. Let's see. Yeah, that's right. I need to subtract here, don't I? This should be minus 2 to the 7th minus 1. Okay, that's going to help. I need to subtract here the same number that I added up there to undo my operation. All right. All right. This mantissa here, that instead of coming from the input decimal number, we should be able to get that from the result of my fractional calculation. Okay. Now, how do we recover the original decimal number? Well, here's the exponent, here's the mantissa. You would think that you do something like equals 2 to the power this plus this. Okay. If you compare this with what we have up here, no go. Why is that? Because we didn't, when we did this here to find the mantissa, we didn't subtract, we divided. We divided. So in order to recover this result, I can't take 2 to the exponent minus plus the number. I would need to do this times the number. Okay, and what do we get? All right, now that's even worse. Remember, the original number here was 342. So what's going on here? Now comes the part where you have to remember the 1. We want to add back in the 1 before we multiply. Okay, so instead of multiplying by C55, you have to multiply by 1 plus C55. And there we have 342. All right, so we've closed the circle. We have a decimal number that we can convert to binary floating point. And then we can convert from binary floating point back to a decimal number. And you might wonder, why go through this rigmarole? Well, one reason is that in a computer, there's a fixed place for memory. And here, you always have the same form for your number. No matter what number it is, you can always put it in the same size box. So that's a good thing. Another thing is that the accuracy for this representation is way, way greater than the ordinary binary representation. And let me show you an example of that. Suppose for this number, let me see if this is still set up. Suppose I have here the number 0.001123. Okay? All right. That gives me this binary number here. And notice that it's mostly zeros because and that's not surprising because that number is very small. All right, now this binary number, I want to convert this back and see if I lose anything in the translation. Now, this one's no longer linked up there, so I have to link them. So here I'm going to put equals this bit, and then go to the right like that. And we'll do fill right. I don't think you can see it, but that's edit, fill right, like that. Okay, so now these digits are equal to that. And let's see what the conversion is. Okay, it says 0.0009, and the original was 0.001. Not too good. If I go even smaller, like this, okay, and I give my output, let's see, did this actually work? This is 0.0009, this is 0.001. If I go even smaller, let's see how small we can go here. Okay, if I do that, then out I get 0. Okay, I've completely lost any accuracy that I started out with. Right? Right. So let's compare this with our result for floating point binary. So this number was 0.0000123. Let's go back down here and do this with floating point binary. 0.00000, whoops, missed it. 0.0000123, and see how this does in our floating point representation. Now notice that in our mantissa there aren't many zeros at all. I'm capturing a lot of the information. Right? Let's go down and see when we try to convert this back again. You can verify that this is the same as the result here because these are properly linked. Right? Now when it converted it back to a decimal number, because the spreadsheet uses scientific notation, it converted it this way, 1.2297. And here I had 1, 2, 3. If you convert this to scientific notation, this is times 10 to the minus 1, 2, 3, 4, 5. And that's what this is saying. This is approximately 1.23 times 10 to the minus 5. A huge increase in accuracy. An enormous increase in accuracy. What's more, if I take a very large number, if here I input a very, very large number, okay, I'm not sure. Well, let's see how that works out. That may be too big. That may be too big even for the floating point. Let's try something a little bit smaller. Okay. If I find out the conversion back again, look at what it gave me. The problem is that the conversion in this conversion is limited only to about 2,000, and I put in 30,000. So I'm out of luck. Right? What happens if I put this 30,000 into my floating point conversion? 30,000. Okay. And then it does my calculations over here, and comes out down here, and look at what I got. My floating point represented the number without any error whatsoever. Well, there is some error, but it's not something that you would see. Okay, very, very small error. Okay, floating point terrifically increases your accuracy. Okay, one more point I'd like to make. I said something about the machine alpha, the machine epsilon. I'm sorry, and the machine epsilon is the smallest number that can be represented. So let me do that. Okay, I'm going to make some space here to show the machine epsilon. So here we go. I want to put some space here. I'm going to select these cells, and what I'm going to do is I'm going to insert cells, and I want to shift the cells to the right. Okay, so this gives me a place to put the machine epsilon. Okay, now how am I going to compute the machine epsilon? Well, as it says in the text, the machine epsilon is going to be the smallest number here that I can represent. So I'm going to make this exponents all zeros. All right. No, I'm not going to be able to do it that way. I'm sorry. Instead, let me do it this way. Notice that there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 places here. This place corresponds to 2 to the minus 1, 2 to the minus 2, 2 to the minus 3, 2 to the minus 4, 2 to the minus 5, all the way up to 2 to the minus 11. 2 to the minus 11 is my machine epsilon. As it says in this file here, the machine epsilon is actually equal to the number of bits. I can't find it right now, but there's a place where he says that the machine epsilon is equal to the number of bits used for the mantissa. Okay. Okay, yes, so here, see, this computer uses 4 bits for the mantissa, and the machine epsilon is 2 to the minus 4. All right, so I can just put my machine epsilon here. It's going to be equal to 2 to the power minus, no, it's the number of bits in this mantissa. In order to count the number of bits, there's an Excel function called count. And I'm going to count all of the values here. There are 11 values. I'm doing this because if I change my spreadsheet somehow, then this formula only needs to be modified slightly. Okay, and there's my machine epsilon. What that means is that that's the largest percentage error of a floating point representation, as long as the number is not way, way too big and the exponent goes out of range, or the exponent is the number is way, way, way too small, and the number goes out of range. But that's not easy to happen. For instance, if I go 0.000000135, okay, let's see if that works. You see, it's still way down to 10 to the minus 8th. I'm going to have to go all the way down to maybe about 20 of these to make it not work. Okay, see, it still works. Okay, you can try and see, try to break it if you want, and let's see how far we can go up. One like this, see if that still works. You can see it still works with a very, very small amount of error. You can see here it's only 0.000, error of 0.0003, relative error of 0.0003, which is less than the machine epsilon. Okay, thanks for listening.